last class we discussed that how we can find out the elastic constants of equivalent soil spring using cyclic plate load test data and then block vibration test data. In block vibration test data we saw two type of tests, that is vertical vibration test and another one was horizontal vibration test. So today let us try to first take an example based on cyclic plate load test data and then see that how we can find out various constant, spring constant from this cyclic plate load test data. So the statement of the example is that a cyclic plate load test was carried out at a depth of 3 meter using a 30 centimeter by 30 centimeter test plate on a deposit of silty sand to estimate the elastic coefficient for the design of compressor foundation. Then in the last class we saw that there were three types of machine, and in that when we were discussing the salient features of them, we saw that reciprocating machine is to be used for compressor foundation. So you see here we have to design a compressor foundation, so that is that machine will be reciprocating machine. So the statement of the example says that plot the stress versus elastic settlement relationship and determine the values of Cu, C tau and C phi for 10 meter square base area. The data obtained from the test was, since it is cyclic plate load test, so loading and unloading and then reloading is there. So you see for the first loading step, when load intensity is 25 kilonewton per meter square, the corresponding settlement recorded was 0.5. When it was unloaded, the settlement recorded was 0.4. Then again in the second step, for 50 kilonewton per meter square, the corresponding settlement is 0.95 millimeter, and the second unloading cycle the settlement is 0.8 mm. Likewise, for 100 kilonewton per meter square load intensity, settlement observed was 2.5 millimeter, and then in this unloading cycle when it was unloaded from 100 to 0, the corresponding settlement obtained was 1.9. Likewise, it has been given for 150 kilonewton per meter square to 200 and 250, and then corresponding settlements are given. What we have to do is, first we have to plot the load intensity versus elastic settlement curve, and then we have to estimate the equivalent spring constants or coefficients, that is Cu, C tau and C phi. So first let us try to find out that how we can estimate the elastic settlement corresponding to each loading intensity. So from the data, the values of elastic settlements they can be calculated. You can see here that when this maximum loading intensity of 25 was there, then the settlement obtained was of the was 0.5 millimeter, and when this loading intensity was 0, then the settlement was 0.4. That means that the recovery, that is 0.1, that is the settlement corresponding to the maximum load intensity to the and the difference to the settlement corresponding to the loading intensity equal to 0 will give us the value of elastic settlement for that particular loading cycle. So in this case, corresponding to this load intensity 25, elastic settlement is 0.10. You can see here that this is 0.5 and 0.4. So the difference of these two is 0.1, which is the elastic settlement in case of this 25 kilonewton per meter square. However, in case of 50 kilonewton per meter square, you have to see that corresponding to this 50 kilonewton per meter square, the settlement is 0.95 millimeter, and when it is when it has been brought down to 0, the corresponding settlement is 0.8. So here it is the recovery is 0.15, 0.95 minus 0.85. Correspondingly, you can find for each loading cycle and tabulate them in this manner. So, to correlate with the previous table and this table, elastic settlement can be obtained by the difference, taking the difference of the settlement at the maximum loading intensity and when it has been brought down to 0. So, for 25 kilonewton per meter square, this elastic settlement of 0.10 mm was observed. However, it was 0.15 in case of 50 kilonewton per meter square, and so on. You can see here that for 150 and 200 it is 1 mm, and for 250 kilonewton per meter square it is 1.8 mm. Now, we know this load intensity and corresponding elastic settlement also. Let us try to see that how we can plot it and can get the value of the elastic coefficients. So, the plot of load intensity versus elastic settlement. On y axis we are plotting load intensity in kilonewton per meter square, and on x axis this elastic settlement in millimeter has been plotted. So, you know that when the experimental data are there, they do not fall along a line properly. So, you have to take the best fit of that. So, these are the data points which we are getting from this particular table, and those data points have been plotted, and then a line has been fitted such that its slope we can find out. So, its slope will be giving us that Cu for the test plate. Now, as we were discussing last time, that when you are finding out this these constants in the field, and then if you are applying them in case of foundation, you have to apply some correction measure, because their values they were depending on the contact area of the block foundation and the soil. So, in case of test plate, the test plate is of a definite size like 30 centimeter by 30 centimeter in this case. However, the area of the foundation can be quite high, and in the statement of the problem it has been given that we have to get the these coefficients or constants for base area of 10 meter square. However, the base area of the test plate is 0.09 meter square. So, we have to convert this value of Cu which is for the plate to corresponding value of the foundation, so that we can use this data confidently as far as analysis of the foundation is concerned. That how we can do that? You know that we discussed last time these formulas, that Cu1, that is the spring constant correspondingly for the foundation. Cu is for plate, A is area of the plate, and A1 is area of the foundation. So, we know this Cu from this particular curve. We have the area of the plate, that is 0.09 meter square, and then A1, that is area of the foundation or base area, which is 10 meter square, that is given. Then once we know this Cu, then you know that this is an empirical relation between Cu and C tau, as that Cu is equal to 1.5 to 2 times C tau. Now, let us say that for this particular example I consider Cu to be equal to 2 times C tau. So, correspondingly C tau will be equal to half of Cu. So, knowing the value of Cu for the test plate, I can get this value of Cu for the foundation. Once this Cu value is known to us, we can substitute here in this particular expression and can get the value of C tau. Then again we know that C phi is equal to 3.46 C tau. All these things we have already discussed in the last class. So, if this C tau is half of Cu, so you substitute this particular expression here in this expression, that will result into 1.73 times Cu. So, using these three relations, that is this one and this one, we can get the value of Cu for the foundation from the value of Cu which we have found out for the test plate. And then once we know this Cu1, that is Cu for the foundation, using this expression we can get corresponding C tau, and then using this particular expression we can get corresponding C phi. You can see here in this that area of the plate which is used is 0.3 into 0.3, because the size of the plate is 30 centimeter by 30 centimeter. So, in meter it will be 0.3, and which will result into an area of 0.09 meter square. So, for the area of 10 meter of base, you can get using this particular expression as this Cu value 15 into 10 to the power of 4 that we have observed or we have obtained from the load intensity versus elastic settlement curve for the test plate, that has been converted it this here in this particular manner for the foundation. So, this is what is Cu into this area of the plate divided by the area of the foundation base, which is 10 in this case. Let us say if it is more than 10, then you have to restrict it to 10. So, this expression, I mean if you solve this, then you will be getting this value of Cu to be equal to 1.42 into 10 to the power of 4 kilonewton per meter cube. Then using this particular expression, that is C tau is equal to 0.5 times Cu, I can get here that 0.5 times Cu, which is Cu is this value now 1.42 into 10 to the power of 4. So, then this will become 7.1 into 10 cube kilonewton per meter cube. Similarly, we have this expression for C phi, which is equal to 1.73 Cu, and Cu we have got as this 1.42 into 10 to the power of 4 kilonewton per meter cube. And so, substituting this particular value here in this expression, you will be getting the value of 2.46 into 10 to the power of 4 kilonewton per meter cube as C phi. So, I hope that now you can appreciate more that how we can get these equivalent soil spring constants or coefficient using cyclic plate load test data, because in cyclic plate load test what you will be getting as raw data is that loading intensity and corresponding settlement corresponding to each loading cycle and each unloading cycle. So, from there we can find out the elastic settlement, and once we plot that elastic settlement with loading intensity, with corresponding loading intensity, and then if we fit a best line to that data, then we can, the slope of that line will give us the constant Cu, which will be there for test plate, which can be converted for the foundation. Depending on whatever is the area of the foundation, you can get the value of Cu for foundation, and then using the available empirical relations further you can get the other elastic constants like C tau and C phi. Now, as we were discussing that in all the system existing in the nature, everywhere some or other amount of damping is present. There is no system in which the damping is not present. So, that is why damping becomes an important parameter as far as machine foundation or dynamic analysis of any structure is concerned. Since this machine foundation, they are subjected to dynamic loads in addition to static loads. So, there damping plays an important role. Let us try to see some of the salient points related to this particular topic, that is damping. Damping in the soil foundation system affects the response in the inverse proportion at resonance, but is practically inconsequential in the non-resonant range of machine speed. So, we have to really see that during the resonance, when the amplitude becomes almost infinite, so the damping effect is in inverse proportion. It assumes importance in the transition period where the machine speed has to pass through one or more of the resonant or natural frequencies of vibration of system during starting or shut down the machine. You see, when you either start or shut down the machine, what happens is that when the machine picks up its speed, it crosses some of its natural frequencies. So, at that particular point of time, whenever it is crossing that its natural frequency, then at that time the damping becomes quite important. In the case of block foundations, damping is contributed almost entirely by the soil, so that its value depends much on embedment of the foundation. You have seen that in case of block foundation, what has been done is that a concrete block is casted, and on top of that motor and the machine, they are mounted, and its mass is also very heavy. So, since we are discussing the case for block foundation, in block foundation this damping which is there in that system will be mostly contributed by the soil on which the concrete block will be resting. So, obviously you will not be putting the block just on the ground surface, you take some depth of embedment. So, depending on that depth of embedment, that what exactly is the depth of embedment, what exactly is the soil cover that is present above the concrete block, depending on that the damping will be there. So, damping in framed foundation also increases considerably due to participation of soil. We saw last time that 3 types of foundation were there. One was this block foundation, then box foundation and wall foundation, that was or framed foundation. So, in that case also this damping is mostly contributed by the soil which lies beneath the concrete slab. Then experimental studies have shown that damping does not vary too much with the type of foundation, that is whether it is block foundation or frame foundation or with the material of construction. So, whatever is the material of construction, be it concrete or any other material, or whatever is the type of foundation, be it block foundation, be it box foundation or be it wall foundation, the damping does not vary with these type of different foundation and material of construction. The raft and pile foundations also do not show too much difference in damping. So, whether it is raft footing that you are providing as foundation or you are providing piles as foundation, whatever is the damping, it does not make much of the difference. It is therefore usual to consider a damping coefficient of about 6.5% in the design of machine foundation. Since the amount of damping is not dependent on type of foundation, its type of construction material, whether it is raft foundation or pile foundation, that is why usually it has been seen that if you consider a damping of 6.5%, that serve the purpose for the design of machine foundations. Now, we have to really, now we were just talking in the qualitative terms, this damping, we have to quantify it, that how we can find out that what exactly is the damping in any particular system. So, to this damping is being represented quantitatively by this damping factor zeta. So, to when you determine this damping factor zeta, that gives you the measure of damping, that whatever is the percentage of the damping or amount of damping which is present in any particular system. So, there are basically 2 methods for determining this damping factor zeta, and they are given in the Indian Standard Code of Practice, that is IS 5249/1992. One method is based on forced vibration test and the other on the free vibration test. So, first let us see the what exactly is the method which is based on forced vibration test. The displacement amplitude versus the exciting frequency curve has to be established by exciting a block or the foundation by a mechanical oscillator driven by a motor. In the last class, we discussed various features of this block vibration test, whether it was forced one or free one. In that one, we saw that ultimately what we get is that this amplitude versus the frequency curve, and from there for corresponding to the peak amplitude, what was the frequency that we were calling as the natural frequency of that particular system. So, in this case we get this particular curve which we get by exciting the block or the foundation on which this mechanical oscillator and the motor has been mounted. The width of the resonant peak in terms of frequency difference, say f1 minus f2 at 0.707 of the peak amplitude of displacement and at the resonant frequency f and z are determined. How it is more clear in this particular figure, that you see that this one is the curve that you will be getting using that forced vibration test. Now, as this statement says that the frequency difference f1 minus f2 at 0.707 of peak amplitude of displacement. So, if xm I represent as peak amplitude of the system, corresponding to that whatever is the frequency that we are calling as fnz, that is the natural frequency of the system. And then if I divide it by square root 2 or multiply it by 0.707, it is one and the same thing. So, corresponding to that you will be getting two frequencies. You see here this xm is here, that is which is peak amplitude, and you divide it by square root of 2 or multiply it by 0.707, it will get reduced to this particular level. And if you draw a line which is parallel to this particular frequency axis, then that line will be intersecting this particular curve at these 2 points. One point is this, another point is this. So, corresponding to these 2 points you have two frequencies, one is f1 and another is f2. So, the difference of this f1 and f2 is used as to determine the damping factor as by this expression, that is zeta is equal to f2 minus f1 by 2 fnz, where f2 and f1 are two frequencies at which amplitude is equal to xm by square root of 2, where xm is the maximum amplitude and fnz is the frequency at which the amplitude is maximum, that is resonant frequency. So, once we know the amplitude versus frequency curve, we can find out this fnz, which is the frequency corresponding to the maximum amplitude. This frequency is also known as resonant frequency, and then we know the peak amplitude. If we reduce that by 0.707, then we get correspondingly two frequencies, that is for one amplitude there are two frequencies, and the difference of those two frequencies divided by 2 times this natural or this resonant frequency of the system will give us this damping factor, which is a measure of the damping. Then method which is based on free vibration test. In this method, the block or foundation is pulled and released suddenly, and the free vibration recorded is obtained by means of a suitable recording and acquisition system. See, as the name suggests that in forced vibration system, the oscillator was mounted to give the excitement to the system, that was a forced vibration system. However, in this case simply this block or foundation, whatever it is just pulled and then it allows to settle or deform, and that condition we know that it is the free vibration condition. So, when it is undergoing that free vibration, we provide some suitable measure to record this vibration, that how it is vibrating, what exactly is the amplitude, what is the frequency, etc. Then the amplitude decay curve is then plotted. As you know that some amount of damping is always there in any of the system, be it forced vibration system or free vibration system. In free vibration system, we know that the system vibrates under the influence of the forces which are inherent in it. There is no external exciting force. So, whatever is the inherent force, once this block or foundation has been displaced, then it will be vibrating under the forces which are inherent in it. So, under those forces the amplitude of the that particular system will go on decreasing with time. So, that amplitude decay curve can be plotted because suitable measure has already been provided to record this amplitude. Then ratio of successive peak, that is x, of the amplitude record is then a measure of damping. So, you will get successive peaks and downs also for that. So, the ratio of successive peaks of the amplitude gives you the measure of damping. How it is, let us try to see with the help of this particular figure. You see that this is the amplitude decay curve. Here is that this is the frequency of the system, that is damped frequency, and this is the amplitude of the vibration on y axis. So, you see here with time this amplitude goes on decaying. So, and then it is the sinusoidal vibration which is taking place. So, you see here this is a one peak and this is another peak. So, and this is another one. So, if I call this as xm plus 1, that is the amplitude corresponding to this particular peak is xm plus 1 and the previous one as xm and this as xm minus 1, then we can find out the damping factor by using this particular expression as 1 by 2 pi log of E xm upon xm plus 1. Or let us say if you are here, you had 3 peaks, that is xm minus 1, xm and xm plus 1. So, either you take these two or you take these two, it is one and the same thing, where xm and xm plus 1 are the amplitudes, like I have shown you here. This is xm plus 1, the amplitude, this much amplitude, and this much amplitude, that is xm. So, using this expression you can determine the damping factor, which is a measure of damping. So, you saw that how we can quantify this damping using this forced vibration test data or free vibration test data. Now, let us try to take an example and try to develop some more understanding as far as the measure of this damping is concerned. Here I am taking one example for this free vibration record. So, the successive peaks from a free vibration record obtained from initial displacement, that is sudden release test on a block resting on soil, are tabulated. I will be showing you in the next slide. Compute the natural frequency of vibration of block and also the damping in the foundation. So, you have to remember that it is free vibration test. So, in free vibration test, the two successive peaks of the amplitude, the difference gives you the difference of these two gives you the magnitude of the damping factor. So, how it is done? This is the data which has been supplied with the problem, that with time, you see the time is increasing from 0 to 0.02 seconds, 0.04 seconds, 0.06, 0.08, then 0.10, 0.12 and then so on till 0.30. And the corresponding peak, you see first at time t is equal to 0, since it is free vibration test. So, at time t is equal to 0, the foundation was just pulled and then it was released. So, at time t is equal to 0, the amplitude was maximum. You can see here that it is the peak amplitude in millimeter, which is 16 at time t is equal to 0, and then it will that since it is sinusoidal. So, next peak you will be getting in the negative direction. So, that is why this negative sign has been shown here, that is the next peak which is in negative direction is minus 12, the amplitude is 12, magnitude is 12. So, and then again you will be getting a positive peak which is 8, then minus 6, 4, minus 3, 2, again minus 1.5. So, likewise you are getting positive and negative peaks, and you see that as this time is increasing from 0 to 0.3, you see here the peak was 16 mm, however here at 0.30, that is at time t is equal to 0.30 seconds, you have peak amplitude of the magnitude of 0.1 millimeter only. So, you see how much is the difference. So, why exactly is this difference is occurring is due to the damping which is present in the system. How we can measure that? Let us try to see that interval between positive or negative peaks. You can see here that these are the two positive peaks. So, the interval here between these two positive peaks, it is 0.04. Likewise, for negative peaks also you can see here that the time interval is 0.04 seconds in all the cases. So, the time period of vibration of block, which we represent usually by t, becomes 0.04 second. Now, we can find out the natural frequency of vibration of block by inverting this particular time period, which is 1 by t, and that becomes 25 hertz. So, amplitude ratio between successive peaks of same sign, that is x1 by x2, becomes 2. You can see here that two successive peaks, if you take the ratio, that is 16 by 8 becomes 2, 12 by 6 is 2, again 8 by 4 is 2, you take this one 2 and 1, the ratio is 2, then 1.5 and 0.75, the ratio is 2. So, the amplitude ratio between successive peaks of same sign, see, you have to keep in mind, because then only it is crossing its equilibrium position. So, x1 by x2 is working out to be 2 in this case. So, we can find out this damping coefficient or damping factor using this particular expression, that is 1 by 2 pi log base E x1 by x2. This x1 by x2 from the data we have got to be equal to 2. So, this zeta will be working out as 0.110. So, if we talk in terms of percentage, so damping in the foundation block is thus 11% of critical viscous damping. So, I hope that you got the idea, got the feel that how the test result from this free vibration test can be utilized to get the magnitude of the damping which is present in the system in the form of this damping coefficient or damping factor, and then it can be converted into percentage of critical viscous damping. Now, let us try to see that what are the various degrees of freedom of a block foundation. As you know that when we defined the degrees of freedom, what was the definition? Was that how many number of independent coordinates that you require to define a particular location or the system of vibrating body. So, the number of coordinates which are required to define the state of any vibrating body is called as its degree of freedom. So, now here we are discussing the block foundation. So, we will be discussing that in what all are the modes of vibration, that is that in what all manner or what all are the coordinates which are required to define the vibration of this block foundation. They will be called as degrees of freedom. For a block foundation, under the action of unbalanced forces, the rigid block may undergo displacements or oscillation as below. As you know that in case of any foundation, it can translate or rotate. Then there are 3 axes, 2 axes in horizontal direction perpendicular to each other, and one is vertical axis. So, there can be the translation along this z axis, which is the vertical axis. See, first I will be telling you about the vertical axis, but because usually we are more concerned about the settlement of the foundation which occurs usually there in the z direction. Then translation along x axis, translation along y axis, and similarly rotation about all these 3 axes. So, rotation along z axis is we call as yawing. Rotation about x axis we call it as pitching, and rotation along y axis is called as rocking. So, wherever I use a term yawing, this picture should come into your mind that there is a rotation which is taking place along z axis, that is which is vertical axis. So, 6 degree of freedom as far as the action of under the action of this unbalanced force are concerned, they can occur. That 6 type of this deformation can take place, which is the translation along the 3 axes and the rotation along 3 axes, out of which the rotation about the vertical axis, that is z axis, is called as yawing, rotation along x axis is called as pitching, and rotation along y axis is rocking. Now, how it looks like in 3D picture, let us try to see. This is what has been obtained from IS 2974 1982, which deals with the various aspects related to machine foundation. You can see that here is the 3-dimensional plot, that is block, and this direction is your x direction, that is in horizontal plane. Perpendicular to this is y direction, and then vertical direction, which is z direction, is this. So, we have the translation along these 3 axes. So, you can see first if I take z axis, which is pz, that is this is vertical one, that is pz, then lateral one is px, which is in this particular direction. You can see here that this is what is your x axis, this is y axis and this is z axis. This point O is the CG of this particular block. So, this any translation which takes place along this particular axis x is lateral transition, and along y axis, which is this py, it is longitudinal one, then along vertical axis it is pz. Then rotation about this x axis, that you can see by this manner from this arced arrow, that is mx, that is a moment which has been applied along x axis. So, this will cause the pitching motion of the block foundation. Then along y, that is this will cause a rocking motion of the foundation, and along z axis, if it is rotating along z axis, that is in horizontal plane, then the motion is called as yawing. Okay. So, you have to keep in mind that whenever we use these terminology, whether lateral, longitudinal, vertical, pitching, rocking and yawing, you should be able to make out that what exactly we are talking of. Yawing is the rotation about z axis, pitching is the rotation about x axis, however, rocking is the rotation about y axis. So, the rigid body displacements of the block can be resolved into these 6 independent displacement as we discussed, that is the translation and rotation about the 3 axes. Now, out of these 6 types of motion, translation and rotation along vertical axis, which is z axis, can occur independently of any other motion, that is either the translation in x and y direction or the rotation in x and y direction. So, the translation and rotation along z axis, they can occur independently of any other kind of motion. Then translation about x axis or y axis and rotation about y axis or x axis. So, 2 combinations are there, translation about x axis and rotation about y axis, and another combination is translation about y axis and rotation about x axis. They are coupled motion. Thus, the analysis of block foundation requires consideration for 4 types of motion. Out of these, 2 are independent and 2 are coupled. As you see, just now saw that the translation along z axis and the rotation along z axis, they are independent, and then these 2, that is translation about x axis and rotation about y axis, and translation about y axis and rotation about x axis, they are the coupled one. So, you have 2 independent and 2 coupled this motion for the analysis of block foundation. So, for estimating the natural frequencies of vibration in the coupled mode, the natural frequency of the system in pure translation and pure rocking need to be determined, right. So, since the thing is that when you are talking of that rotation about x or y direction, either pitching or rocking will come into picture. So, since they are coupled motion, first we need to know that what exactly is the natural frequency in only translation, that is pure translation and pure rocking condition. How we do that we will see in subsequent slides. But further, as the state of stress below the foundation block in different modes is different, the corresponding spring constants to be used. You must be wondering that why we are so much intent to find out the natural frequency in all different types of vibration or the mode of vibration. Because you know that depending on the mode of vibration or depending on the degree of freedom, you have to get the corresponding equivalent spring constants. So, first we have to identify that which type of motion is being there, and then what are the different combination that can be there. So, for all the combination, we have to get the corresponding equivalent spring constant, so that we can find go ahead in the analysis procedure. Now, before finding this equivalent spring constant, for that you need to know the natural frequency corresponding to each and every motion type. So, that is what we are attempting here. So, first let us try to have a look that what will be the natural frequency, or how we can estimate natural frequency as far as vertical vibration of a block foundation is concerned. You can see here that you consider this block of contact area which is A embedded up to a depth df below the ground level. So, you can see here that this is the ground level and this block is embedded as df. Now, why I have put here as df is equal to 0? Because you know, when you analyze, then you have to make some assumption to make the analysis simpler. So, to make the analysis simpler, this df has been assumed to be 0, which I will be explaining you in the subsequent slides when we will discuss that. And then this block is subjected to this force, that is P naught sin omega t. So, this is what is the physical system, that this is the soil which is lying here, and with some embedment depth the block is being casted, which is subjected to the external force which is P naught sin omega t. Now, as I told you that this soil can be modeled as the springs, the series of springs. So, how it is idealized has been shown in this particular figure, that this soil, this particular soil which is lying below the block has been replaced by equivalent springs of stiffness Kz. See, we are talking of vertical vibration of a block foundation. So, vertical direction is z direction that we are considering. That is why this subscript z is coming into picture here when we are talking this stiffness of these springs. So, this Kz is the stiffness of the spring which are representing the soil which is lying below this block. This block is having the mass m. So, if you remember that in one very first lecture we discussed that linear weightless spring mass system. So, we have tried to idealize this whole physical system with the help of these spring and mass system, and then this mass which is representing this particular block, this mass m is subjected to this external exciting force of magnitude this P naught sin omega t. Now, let us try to see that how we can analyze this particular system and can get the natural frequency of this system. For simplicity of analysis, it is assumed that block is located at the ground level such that there is no embedment, that is df is equal to 0. So, as I was explaining you earlier that just to make the analysis simple, this embedment depth has been assumed to be 0. However, for all practical purposes this depth of embedment is not 0, but usually for theoretical point of view we have to assume some simplification to get the analysis more simpler. Now, you see that the picture which was in inverted form in this particular manner can be simplified here like this, that this is the rigid base and then this is the soil, mass is there and which is subjected to this load P naught sin omega t. So, the subsoil is assumed to be replaced by an equivalent spring with spring constant Kz, which you can see here that it is representing you the subsoil, m is the block or the foundation, that is with mass m, and P naught sin omega t is the external force which is acting on this particular block. So, assuming that an unbalanced force acts through the center of gravity of the block, and by neglecting damping, the equation of motion of the system can be written as mz double dot plus kz into z equal to P naught sin omega t. If you remember that in very first lecture we discussed it how we can get this particular equation, that is summation of all the forces were equal to the mass into the acceleration. So, you can see here that this was the external force, this is the force which will be there in the system due to the spring which is representing the subsoil with this stiffness kz. So, and this m into z double dot is the acceleration, which is the differentiation of z with respect to time, that is twice if you differentiate z with respect to time you will get this z double dot. So, this m z double dot plus kz into z is equal to p naught sin omega t becomes the equation of motion in the absence of damping, where m is mass of the foundation block including the machine, kz is your equivalent spring constant of the soil in vertical direction for the base area A. And you know that that the different coefficient that we found out was Cu, C tau, C psi and C phi. So, from the definition of those we can get the value of this equivalent spring constant as Cu into A, where Cu is coefficient of elastic uniform compression. So, in this case if you try to solve this particular equation as we have already done in first few lectures, then you will be getting the natural frequency of the system which is f and z as 1 by 2 pi square root of Cu into A by m, where this Cu into A, see it is as similar to the force system in the absence of damping. So, that would have, it was there, we saw earlier that it was 1 by 2 pi square root of k by m, and here k is equal to kz and that is equal to Cu into A. So, I am simply replacing that particular expression and the natural frequency in that case will become 1 by 2 pi square root of Cu A by m. Similarly, the amplitude of the motion, that is Az, will be given by this particular expression, that is P naught sin omega t divided by Cu A minus m omega square. Now, if I take this m to be common, so this will become that Cu A by m, and that Cu A by m, you can see here that this Cu A by m becomes 4 pi square f n z square, and 2 pi into f n z is nothing but omega n z. So, that is how you are getting, once you take this m common out of this particular bracket, you will be getting m omega n z square minus omega square. So, your Az, the expression for Az will become P naught sin omega t divided by m into omega n z square minus omega square. So, this is how you can find out the natural frequency and the corresponding amplitude for vertical vibration of the block foundation. And then in case we want to find out the maximum amplitude, so maximum amplitude will occur when the sin omega t is equal to 1. So, that will become P naught divided by m omega n z square minus omega square. So, a small value of damping has practically negligible effect on the natural frequency, that we have already seen when we were discussing that forced system and free system. There we saw that damping if the damping value is quite small, it has negligible effect on the system. Now, this was what about that vertical vibration of the block foundation. Now, if we see that rocking vibration of a block foundation. So, rocking vibration means that you are applying the rotation along y axis. So, you can see here in this particular figure that if it is a block, this is your z direction, this is x direction, and in this particular direction you have this y direction. So, a block foundation with area A resting on the ground surface is acted upon by a moment my, which is equal to m naught sin omega t about the y axis in xz plane. So, you can see here that this is what is your xz plane, and in perpendicular to that, if you apply the moment, the rotation of the block will be taking place in like this manner, which has been shown by the dotted ones, and then if this angle is equal to phi, that is the rotation angle is phi. So, how we can analyze this particular situation, because you have to get the corresponding value of soil spring constant, and for that you have to first get the natural frequency when this particular type of vibration is occurring. So, the foundation block is assumed to be symmetric about y axis. It is further assumed that the center of inertia of mass of the machine and foundation and the centroid of the base area lie on a vertical line through the center of rocking vibrations O. You can see here that this is what is the center of the vibration, that is O. Then considering moments about the center of rotation of the block, we get the moment due to the soil reaction to be equal to minus C phi into I into phi, where I is the moment of inertia of contact area about an axis which is passing through the centroid of base contact area. Then moment due to displaced position of center of gravity of the block is mw, let us say, which is equal to w into L into phi, which is acting in clockwise direction. That is why we are putting it with minus with positive sign here. However, here we put that negative sign, that means that it was acting in the anti-clockwise direction. As you saw that in case of the translation, we were taking the equilibrium of forces. However, here since we are subjecting this particular system to the rotation along y axis, so that is why we will be taking the moment equilibrium, and that is how we are trying to find out that what exactly are the different moments which will be there when this is subjected to the rotation about the y axis. Then externally applied moment, you know, it is my, which is m naught sin omega t. So, the equation of motion about the center of rotation can be written as mo phi double dot is equal to summation of m. Summation of m gives you the summation of all the moments, where phi double dot gives you, since here it is you must be wondering that why it is not z double dot here. See, in earlier case it was translation, so that z was coming into picture. However, in this case the deformation is rotational mode. So, it is the angle which will be coming into picture, and it was getting displaced by an angle phi. So, you have to differentiate phi with respect to time to get this quantity, that phi double dot, where mmo is mass moment of inertia of the machine and foundation block about the axis of rotation. So, by putting all the moments in this particular equation, we will be getting this particular expression. This is the external moment. Then we had the moment, as I told you earlier, that C phi I into phi, which was in anti-clockwise direction, and plus W L phi, which was in clockwise direction, and that will become equal to the internal one, that is the moment and whatever is the acceleration because of that, that is mmo into phi double dot. And this equation can be rewritten in this particular form, and if you solve it in the usual manner as you have already done in case of vertical vibration of the block foundation, then you will be able to obtain the natural frequency of the system, which is represented by omega n phi to be equal to square root of this C phi I minus W L divided by mmo. So, this is how that you can get the natural frequency of the system. So, the maximum displacement A phi is given by, that is A phi is equal to mo divided by mmo omega n phi square minus omega square. Now, usually in practice it has been seen that C phi I is quite greater than WL. So, you can neglect this particular term, that is C phi I, it is quite high. So, you can neglect this WL term in this particular expression. So, if you do that, the resulting expression you will get here as C phi I by mmo, or that natural frequency that you can get as 1 by 2 pi of omega n phi, and that will be this particular expression. So, in this class we saw that how we can get the measure of damping using the damping factor in case of free vibration test and in case of forced vibration test. And after that we saw that how we can go for the analysis of block foundation, and in that we saw that there are basically 6 degrees of freedom, that is translation and rotation about the 3 coordinate axes x, y and z. However, out of them we saw that there are 4 independent vibration modes, out of which 2 were independent to each other and then 2 were the coupled motion. So, it became necessary for us that what exactly is the natural frequency corresponding to all of these vibration mode to evaluate the corresponding equivalent spring constant. So, we saw in that sequence we went ahead and then we saw that how we can get the natural frequency and the maximum amplitude for vertical translation of block foundation and for this moment about the y axis, that is the rocking motion. So, and the subsequent one, that is the remaining ones, we will see in the next class. Thank you.
Thank you.